Hi friends, let's look at the second problem about sentence similarity, that is sentence similarity 2. In this video, we're going to solve this problem using UniFind. So for this problem, actually you can also solve it using a graph method like breadth first search or depth first search to get connected component induced by the by the similarity pairs in this problem. But here we feel that the UniFind is very natural to this problem. So we are going to write two formats of solutions based on UniFind. So in other words, we use the same method, but we demonstrate two formats or two paradigms to use UniFind. So here, in order to make to do the problem in an efficient way, it's very important to understand the problem statement. But in view of time, we're going to emphasize one thing. So here we see that the two sentences are similar. So if they have the same length, and also each corresponding words word pair is similar. So here the similarity relation defined by the similarity pairs has this following property, and that is transitive. So first we need to know a word is similar to itself, and also if A is similar to B and B is also similar to A, this is called reflexive. So here it's also transitive. It means that if A and B are similar and B and C are similar, then we can interpret that A and C are also similar. So this is actually a rigorous definition or the same definition of a similarity relation or a relation in mathematics. So with that said, let's look at three examples to notice that. So here we have a grid, we have fun, right? So so we know great and good are similar, and good and fun are similar. So great and fun are similar. So the first pair is okay. The acting and drama. So acting and drama are similar, so it's also okay. Skills and talent are okay. So this is similar. The two sentences are similar. So this is true. So here also true. We don't want to comment. So here this example, I and I the same. Love and love the same. So lead code and One Piece. So they are not similar. So you can see that this does not exist in this pair does not exist in the similarity pair list. So with that said, so typically if you do the problem yourself, you need to also read this constraint very carefully, because typically the constraint defines the problem size and also some key information. Some of them will actually repeating the main statement, but it also plays the role of emphasizing some points. So here we're not going to read line by line. So now with that said, there are 2 points we want to notice. First, here the similarity is first we know for any word, so itself is similar. The second one is if A is similar to B, and then it implies also B is similar to A. The third one is A is similar to B and B is similar to C, and then it implies A and C are similar. So this is a typical relation in mathematics. So here we are going to use UniFind, right? So there are typically two ways to use it. So one is maybe a harder one. So we are going to use it as a data structure. In a data structure or as a data structure. So we're going to call this is called disjoint set union, right? Disjoint set union, DSU. Or we can just use it as a group of functions. Typically we implement find and the union method or function. So if the two functions are in a class, we're going to we know that those functions are methods in that class. Otherwise, we just use it as a first class functions or common functions. So here, actually, the first way is more modularized, and the second way is actually relatively easier. If we know the universe or the full set at the very beginning, so we actually using the second option is easier. But in order to give you a full account of UniFind, and so we are going to use this one as an example to demonstrate both the two paradigms. So I'm going to first do number one. So I'm going to write a disjoint union and then implement find and union method. So this is actually very straightforward if you practice a lot. So I'm going to use the DSU. So let's initialize it. So I'm going to have a self roots, right? So use it as a dictionary. So this will give a word and its father or parent. So rex. So in other words, so a word and the integer. Maybe it represents the cluster size. For example, the cluster, if words having the same roots or parents will in the same cluster, or in the graph language, you can talk about connected component, right? So those the component size will be the rec. Actually, for this problem, you can interpret it as this, but in a wider sense, so rec can include some other meanings. So this is the data fields and all the initializer. So now let me implement the find method. So given the word, we want to find its root. So here, if we write in this way as a class, we need to notice that. So a word is not necessarily in the data fields, roots or rec at the very beginning. So we need to pay attention to this point. So we are going to do write a if logic. If word not in self roots, what we are going to do? We are going to first add this words into the dictionary or the set information. So we set its root to be itself because we don't know other information yet. So then the rex of this word will be 1 because currently this cluster contains only this word itself. So this is the one case. Otherwise, word is inside this field. Then we can use the typical way to find the root. So you can write in a recursion format, or you write in a while loop. So here I'm writing in a while loop. So we want to return the result. But if the result it should satisfy that its parent or the roots is itself. So we are going to use a while loop. While result does not equal to self roots result. Then we're going to set result to be self roots result. So this is the typical way of writing this one. But for small size problem, this will be sufficient. But in order to quickly find one, so we typically use a trick called path compression, right? So we can apply this twice. Right. So here, let me see. I can write. This is called path compression. So this is for speed of finding the root. So, but typically you can just ignore this one if time complexity is not that rigorous, right? But adding this one, that will be fun. So similarly, we can define the union method. So self word 1 and word 2. So basically, if word 1 and word 2 are similar in this problem, so we are going to set them as in the same cluster or same connected component. So how do we do this? First, let's find the corresponding roots. So because we have already implemented the find method, we can call find method, right? So let's copy this one. So this will be 2, right? So first, if R1 equals R2, they are already in the same cluster. We don't need to do anything. Otherwise, so we can set one is the root of the other, right? So you can set, say, self roots of R2 equals R1. Then we can see rex of R2 incremented by that of R1, right? Because we combine these two clusters. So this is the one way, but this way, so it's the very vanilla way to write this solution. So I'm going to copy this one. So I'm going to make some remark. So this is a vanilla implementation. So I'm going to first copy this here. So then I'm going to copy out this one. For this problem, this copied out code should be fine, but I want to take rec into consideration. So in other words, I'm going to use union by rec. So we want to combine small clusters into the larger ones. So this way we save some time when we do search overall. So if self rex R1 is no less than that of R2. So we're going to do this, right? So notice that because we have called this find W1, so find W2, and then so R1 and R2 are always inside the rex, right? That's due to the implementation of this find method, actually this if part. So that's the one part. So if else, so f else, so we're going to reverse, right? So we copy this one. So here we set, so here this should be, because we set the root of R2 equals R1, we combine merge the cluster containing R2 in R1. So we need to do this. So otherwise we set the root of R1 is R2, then we increment the size of R2. This corresponds to merge the cluster containing R1 into R2. So we increment the size of the rex of R2. So this is an implementation with union by rec. So this will finish this data class DSU. So now we can write some problem logic here. So once we wrote those here, solving the problem will be super easy. First, we initialize a object, right? And then we iterate over similar pairs. So for W1, W2 in this similar pairs. What we do is we call DSU union and W1 and W2. So then this will be actually the main problem logic. So now we check if the two sentences are similar. So we just need to use the definition, right? Check if the two sentences are similar. So notice that this line, though, is this part, though, is very short. Actually, it contains a lot of information, especially the union operation and find operation, right? So now what we want to do, first, if length S1 does not equal to length S2. So by definition, they cannot be similar, so we return false. Otherwise, so we're going to iterate over S1 and S2 simultaneously. So for word 1 and word 2 in, so I use zip function, so S1 and S2, right? So if they are not in the same cluster, in other words, they are not having the same ancestor, so the sentence, the two words cannot be similar, so the two sentences cannot be similar. So if DSU find W1 does not equal to DSU find W2, then we return false. If after this for loop nothing has returned, it means that the two sentences are similar. So we are going to return true. So this is a full solution to this problem. So let me first do a test, and then we can make a small summary. So now if rex1 is greater than self, let's see, self key error. Let me see. Here I forgot to return W. So this is important, right? So that's why you have none here. So let's write here. Unsupported operation, integer self-reg, and self-roots. So in the add, so we need to add self-rex, self-rex, right? Let's test again. Here it passes one example. Now let's look at the generic case. It passes all the generic cases. So here we are using implementation of union by find. Let's comment out this part, and let's use this short one, this vanilla one. So let's test it. So here I still write things wrong because I need to X, right? Yeah. It passes all cases, but slower. Now let me also comment out this part, and then do a test. This still works, but slower, because this is overall it's slower. Should be slower, but this the number does not. This is a statistical power, but not a single run. So now let me add all those, right? So this is the with path compression, and let me comment on this. Then I'll recover this part, right? Let's submit. Right. So this is the one way. So we do something like this. So now I want to write another solution. So here, let me copy this part. So I'm going to change this one to be version v1, right? So now you can actually safely ignore the codes above, right? Then we just ignore everything above logically, right? So we are going to borrow some codes for sure. So we are going to delete this part, right? So now I want to write a solution without using class, but just use common function. So one thing is that when we write the class, so at the very beginning, because we need to initialize this one, we don't know the size, the number of words involved, right? So now here, let's see. So we have the two sentences, and we have they have some words, and also the similarity pairs. Let's first get the all the words got involved. Let's call it a universe, right? So it's a set, and then what I'm going to do is for word in S1. So what I'm going to do is universe and this word. So similarly for word in S2, so universe add words. So this is for pedagogical purpose. You don't need to do this one by one. You can translate this S1 and S2 into a list, and then you just do union of sets, right? That's faster. But writing this way is to help you understand the full logic. So similarly, I can do for word 1, word 2 in this one, right? In similar pairs. So I'm going to do universe and W1. Let's copy this line, right? So up to now, so this one first get all the word involved. Evolved, right? So right, as I commented, you don't need to do this very verbose, but sometimes doing the things in a verbose way is a demonstration of understanding, right? So this now let's write the find and the unit method. So what we do I'm going to do this root. So it's w for word in universe, right? And the rex is originally it's just itself isolated for word in universe, right? So now let's do the find and unit, find and unit. So I'm going to copy those parts. So, but we need to make some modifications. Now it's not a method, so it's a function. I just also we don't need this, right? Because we already the word already in the set. So let me do this and this. So here just the roots, right? So here just the roots, here just the roots. Yeah. If you can follow up to here, actually it will be very beneficial so that you can know how we think of this problem, right? The thought process. So this way, so we got the find method. And also let me copy this unit method. So let me put it here again. So we just have find function, right? And also those are dictionaries, roots and rag, right? So basically the logic will be the same as before, but we don't need to consider this situation here, right? So now we can do the problem. First, let's see, for W1, W2 in this similar pairs, right? So what we want to do is we just call the union function, right? Union W1 and W2. So here notice that the roots and regs are given in terms of dictionary. So those dictionaries are mutable in Python. So when you call this, actually the state of this root actually changes. So let's first finish the problem solution, and then we want to make some comments on how to find the clusters within each word. So now let's solve the problem first. So we're going to copy this part. So this is the same logic, right? So but I just need to do this, right? Just call the find method within the function. Let's test it. The invalid syntax, where it is? Oh, here. So I need to comment out this. So missing var required argument union. Let's see. We need to delete this self, right? So no. Yeah. It passes all the cases. So that's the one thing. As I commented here, so you don't need to do this. Point 1. So universe union equals set of S1. And universe union set S2, right? For the similar pair, actually you can do the same thing, but let me, for simplicity, I'll just keep it here. So let's do a test. The same thing, right? So this is one point. So another point is that you can actually also find all the clusters. So for example, in example 1, let's see. We know great and good are the same, and fun and good are the same. In other words, great, good, and fun should be in the same cluster. Let's find all the clusters. So here, let me, after we do the unions, let's see, extra. So find all the clusters. So in the terms of graph theory, you can see connected components. So this is actually very simple. So you can do clusters. Let's see, a dictionary, right? So what we want to do is, so for we're going to iterate. So for so here we're going to iterate over roots. So for word and parents or root in roots items, right? So then if we first find the cluster name or the representation, so this will be so let's call it root. It should be roots the parents, right? Then what we are going to do is that if root not in clusters, so what we're going to do is clusters, so the root, so we are going to see, we can use another set, right? So see w, add this w. Otherwise, what we do, we know clusters root is a set, so we're going to add this w. Then we just need to return the clusters or print the clusters, right? So let's print out this one. So I'm not sure if we are using first example. Let's see. Yeah, we are using first example, right? So we know clusters and platform, right? We know platform, they have so this is the last one, right? So there are one cluster, 2, 3, 4, because this one include all the words involved. Also, let's print another one. Let's print out the universe. So you will see, right? Yeah, this is all the words involved. So we classify them into, I guess here is 1, 2, 3, 4 clusters. Let's also look at example 1, right? So let me copy this one. So let's run, right? So we just need to make sure, right? Great, good, and fun are in the same clusters. You can see great represents the cluster, right? So the corresponding set is fun, great, and good. It means they are in the same cluster. Also, we know skills and talent should be in the same cluster. You see here, skills and talent. We saw acting and drama are in the same clusters. That's why the first example should return true, right? So I guess up to now, so we have given a rather thorough solution to this problem, and also we give a very thorough explanation or use cases for the UniFind, right? So we give 2 methods or paradigms to use UniFind in this video. Hopefully this video will play some role in helping you understand the UniFind data methods or disjoint set data structure. So with that said, I guess the video is sort of long. I will stop here. Thank you.